We will introduce you at the presentation of the intermediate workshop of Re-APS. Before to explain the context of the Re-APS project, I will show you 3 questions. I suppose because we are very aware people here in the room, but I would like to know if you could answer to these 3 questions. First, in your opinion, what percentage of recycled polyester is used in global polyester fiber production? 10 to 15, 7 to 10, less than 7 if you want to take a picture and recycle polyester. So 7%. It's for the global consumption, production of fibers, included polyester. But if we consider only polyester, the answer is between 10 to 15 of RPT produced, but this polyester is 98 made from, so we have a margin to develop this kind of project, textile to textile. Then, starting in which year must EU member states collect textile separately from other waste streams? Hello. So, 10 participants 2025, it's true. EU member states are required to collect separately from the 1st of January 2025, and it stipulates that at this date textile must not be mixed with residual waste streams. So, the last question. How many tons of textile are sent to landfills or incinerated each year in Europe? So, majority say that it's about 5 to 6 million, and it's true because we produce near to 7 million tons of textile waste per year, and the majority is not recycled. About 85% are not end up in residual waste, so it means 5 to 6 million tons. So, and we know that of this tonnage is polyester, so we have a margin to develop polyester recycling. So that's the reason we have begun this project in 2024 to develop the thermomechanical recycling of polyester to apply in textile or in plasturgy. And this project is part of Interreg 6 program, France, Wallonia and Flanders. And this program is an instrument in the European Union's dedicated border territory cooperation and to build a stronger cross-border project thanks to the use of networks in both sides of the border. And for this period, it's 2021 to 2027, and the priority are innovation, low carbon transition, biodiversity and territorial cohesion. Re-APS is also a project of the portfolio S3, and specifically it represents in POM, Flanderen, and is structured around 4 key areas, building a cross-border network among stakeholders in the 3 regions and developing a common strategy for smart specialization. And the priority sectors identified are the circular economy, sustainable food and digitalization. And we have 7 projects. As far we will send the presentation project, but we are one of this project on the circular economy. So, priority and objectives of Re-APS are supporting business through innovation and applied research, and strengthens R&D capability and innovation, and as well as adoption of advanced technologies. And we have 4 partners and 4 associated partners. Raw materials in this project is the coordinator and manages the cross-border network. Fedustria on the communication, Centexbel and ceci on the technical part of the project. And we have associated partners in France. One is Federation for Textile and Clothes and Apparel in the north of France, UITH. One Team 2 is a cluster to the circular economy and recycling in general. And Refashion, represented here with Léa Lemarinel. It's the eco-organism in France to finance the collection and solution for the textile made put to the market. Then the project is organized around 3 main areas. One is on the preparation for the recycling, thermomechanical recycling, Centexbel. One is on the thermomechanical recycling directly and application to develop in the textile industry, led by CETI. And one is on the development of the network like here today, to exchange with the value chain in textile. And this project, we did a previous project with Centexbel, Retex, in the previous Interreg program. And this project, Retex, was dedicated to 3 value chains in recycling, one in cotton, one in polyester and cotton, and one in polyester. For cotton, polyester and cotton, the focus is to develop a solution for the main fibers produced in the world, cotton and polyester, 78% of the production. And we did the first value chain polyester, cotton and cotton in the mechanical recycling. And we did POC with the actors in the cross-border network, and we have some success, some trials we did in these 2 values. But the third was made at the lab scale, because at this period in 2017, there are not a lot of offer in thermomechanical recycling of textile in general. And so we did some trials at Centexbel, but at the lab scale. And what we were able to identify were some technical barriers. So we did some trials with already some people from here, from Berry Global, Urband, Saati, Maenhaut, if I well remember. And then we identify some barrier for in the first rheological degradation, throughout the process, shredding, compaction, pelletization, the intrinsic viscosity of the polyester rates, making the material more fluid and then fragile once extruded. And a second barrier was drying, because once shredded and compacted, textile fibers cannot be thoroughly dried using current equipment. However, insufficient drying directly accelerates the degradation of the viscosity, creating an impossibility to develop further. So, and some problem aspect of the textile, because as far as this period, the machines were not so available. We had some research to solve the problem of fluffy product, because these machines are usually used for plastic industry. So since the beginning of this Re-APS project, as far as 2 years old, we developed an internet website. We have a LinkedIn, and we are part of the ecosystem. I invite you to see this website, where we can find the overall project in Europe on all circular or sustainable product in textile, in textile market in Europe. And then we have flyers, and we have contacts and some trials made from these different companies in the different regions of the project. So I finished and about the crossroad call, because this call proposed to SMEs to develop cross-border collaboration in this Interreg zone, and you must be minimum 2 SMEs, one from France, one from Belgium. The TRL is high, from 5 to 8. The maximum of budget is about 500,000 euros, and the last project who lasts 2 years. And the funding is important because it's 50%. Voilà. So, and the subject are circular economy, health, digitalization, and sustainability. So now, I finished. Voilà. If you have it after or necessary now, no, it's okay.
What I would like to do today is introduce you in the world of thermomechanical recycling. So you will see later on, we'll present some first tours on the Re-APS project, but I will start with a brief state of the art. Where are we today? What problems we are facing with? And what might be some solutions? Some of those solutions we will further deep dive in during the examples of the Re-APS project, but I will do it more theoretically with some nice examples. First of all, present you some basics. What is recycling? What is still recycling? So also, you could have some discussion. I will then show you some strengths, but also some limitations, and what might be some solutions to overcome those challenges. And then I will also show you some examples, not only what we are doing in the Re-APS, but also in the industry today, what is already possible and what are, let's say, the levels where the companies are using those technologies. I'll show you quickly what we can do at Centexbel, then later on you'll also see what we do in the Re-APS project as an example. So first of all, let us look at the recycling technologies that are available. The focus is on polyester. So polyester is a polymer, can be remelted, and this is what we aim to do here. We try to remelt a polymer matrix and to respin back into textile fibers, fiber to fiber. Where is this placed in all recycling technologies? Of course, the first important thing is avoid that it becomes waste. So also for our textiles, first important thing would say, can we go to reuse? Can we go to refurbish whenever needed? When this is possible, we come into the recycle technologies, and there are options. You can go to what is called mechanical recycling, and here is an important notice for people coming from the plastic industry. Mechanical recycling is also the thermomechanical recycling. For textile materials, we make a differentiation, because what we mean with textiles with mechanical is we just try to destroy the textile structure and go back to the fiber structure. So we try to unravel the material and to go back into fibrous materials to recuperate the fibers as they are. So with some mechanical forces, so that's the reason we call it mechanical recycling. In the loop is what we will focus on today, thermomechanical recycling, because it can happen that the fibers after mechanical recycling are too short and you're losing your mechanical strength of those materials, so they don't have any use anymore. So in that case, we try to go to thermomechanical recycling, where we want to use the polymer, melt the polymer, and go back to fiber spinning. So from fiber to fiber, but with recuperation of the polymers. If this is not working, yeah, you can say, let's go to depolymerizing of our polyester, let's do the chemical recycling, and then the thermal recycling. This is, of course, the pyrolysis processes, where you go back to syngas. The last step in the whole story, you only go to insert. Is it a one-to-one solution today? Probably not. I think this is an important first remark. It might happen that some waste streams are very easy to go maybe to mechanical recycling, then it would make sense to go to the mechanical recycling, because you need less efforts, less chemicals, less heat to transpose this, because every step has so pros and cons, because you're using energy you're using consumables. So it's what is my waste streams, maybe how pure is my waste, and then maybe decide, okay, what is the best way for my waste material. So it's not that one technology will solve all our problems. It will probably be a combination of different technologies. So what we would look like today is the thermomechanical. So as I said, we want to use the polymer and we want to try to recuperate the polymer. So try to remelt it and respin it into a textile fiber. This is a very known technology. It's also the technology you might use to spin a virgin. You also start from pellets and you try to spin a virgin polyester yarn out of a pellet. We want to do the same. If you look recycling, we now today, you see here for plastics, this is already quite well known. So high TRL levels, bottle to bottle, bottle to fiber. You can also, this is also a kind of thermomechanical recycling. So for plastic, we have quite applications where plastic to plastic recycling, plastic to textile recycling is accepted high TRL levels. What we do see for textile materials, if you have your industrial waste material, you know your composition, also there you can see we already at high TRL levels. So a lot of companies are already working with the cut-offs during production, putting them back into production as an alternative feedstock. So internal, clean industrial textile waste, for sure we can deal with it. Main problem comes when we talk about post-consumer materials. And I will show you some pilots, some first installations that are put into place. It will become important what do we consider as post-consumer and how will we sort those materials. Because depending on the sort of those materials, we might be able to reach different quality levels and then also probably different TRL levels. The idea, it's always the same. We start with the collection, we shred our material, depending on what is needed, we will come back to it. We might need to clean and to compact it. You dose it into an extruder, so you remelt your polyester materials, and then you have a pellet, and this is a pellet you know can be replacing virgin polyester pellets. So in theory, it will work for everything that's thermoplastic. So every material that will melt can go to a thermomechanical recycling process. So polyamide, a polypropylene, a polyester. For what will it not work? For your cotton fibers. Of course, cotton fibers are natural fibers, they will not melt. In practice, of course, we will not have, let's say, a mixture of all those polymers, putting them all together into an extruder. Also, this will not work. Every polymer that you do see here has another melting temperature and another viscosity problem. So blending all those things together, no, that's something we would try to avoid. So polymer blends, also some contamination in from the quality of your material. So that's the reason why I also need to say sorting will still be important, and indeed not everything will be processable in a thermomechanical. What do you get out? Of course, your pellets, and with your pellets you can go back to fiber extrusion, but also you can work, and this is something we will show you, depending on your composition, we can try to purify it. So we can try to remove volatile components, non-melted particles can be filtered out, but with certain limits. You will not be able to filter out whatever you want, and taking into account color on the way it's colored might be a difficult challenge. Because if you enter here, let's say, a mixture of the colors, in the end you will have something brown, black, grayish. So also there, sort might be important, but luckily in Re-APS we will also show you some nice examples how to deal with color and maybe a way how to remove out of your materials. Okay, this is the theory, but of course, how do we deal with it in practice? First important thing, if you have a if you have a plastic material, and you try to shred a plastic material, you will have still a volume. If you try to shred a textile waste material, you have something very fluffy. This is the first thing to deal with, and this is bulk dense. I'll show you some examples how to deal with it. Viscosity, I will not go into detail. Very important one to follow up, how to deal with changes in viscosity. And last but not least, contaminations. And why is contaminations important? Not only for your color and that you would not be able to color, but you should also take in consideration legislation. Because you can take back now, let's say, old textile materials that might contain a flame retardant on the market. If you take it back as waste, you have a forbidden additive into your material. It doesn't make sense to put this back on the market. So also here, look at and make sure that your material that you're taking back is REACH compliant. We are also working on another project where we try to remove those materials. Also in Circoplast we are looking for flamer. We will see in the Re-APS how we can combine those different technologies. But let's say a reason why we would choose for this technology, it's a known technology, it's very efficient, it's easy to implement, and in theory you have minimal emissions, so that's definitely the pros why we would consider a thermomechanical recycling. First important challenge, the bulk density. So we try to shred, and here you have a picture of a shredded textile material. That's a huge bunch of materials. It doesn't weigh anything. People that are used to work with extrusion, they will know if you try to put this into a screw, it will dance on your screw, and you need somebody with a stick to really push it into your extruder. This is definitely not the way we want to work on an industrial scale. Maybe here in the lab we can put a stud on it and push it into our extruder, but that's not an industrial way to work with fluffy material. So what you can do, you need to densify those materials. And I will later on show you, when talking about industrial implementations, also some machine builders are really focusing on it. Try to, in one step, shred, densify those materials into the extruder. If you don't have these options, you can work with a separate step. And this is an example of a kind of compacting unit where you start from a fluffy and you use mechanics so you don't melt your material to avoid some kind of breakdown of your polymer chains. You just try with some mechanical force, squeeze it into a pellet-sized structure, and that's easy to dose. So what you can do, also work with adapted feeding systems, and that's later on I will show you the integration shredder extruder. But it needed, why? Because you need a constant throughput. So you need in your extruder, you need to make sure that your throughput is always the same. So that's the reason why you reconsider how to work with bulk density and try to densify your material before you go to extrusion. Second important challenge, viscosity. We are working with polymers, we're working with polyesters. Polyester quite sensitive to hydrolysis. It means that you are try to cut your polymer chain into smaller pieces. When you cut the polymer chain, you lose your mechanical strength. So this is something you want to avoid, and you want to keep, let's say, your polymer chains as long as possible during your reprocessing to make sure you're again able, for instance, to make a high tenacity polyester fiber. What can you do there? Because what will happen if you're cutting your polymer chain? Things like this. You can say, yeah, I have problems with my extrusion is unstable because you have a lot of into your viscosity. You are losing your melt strength because you're losing your long chains, so you don't have any strength in your material. Filament fractures, and this may be underestimated, but if you have, let's say, different polymer chain lengths, you can have something, if you try to dye those material, you can have instant dyeing. Just to show you what an example from a European project where we worked with monofilament extruders. Monofilament extrusion, this is a virgin polyester grade, so with a high IV value, an IV value around 1. And you can see with this, with different draw ratio, we could really reach high tenacity polyester fibers with a virgin material, standard condition. If we try to shift to recycled still bottles, so not yet textile to textile, but if you go from a virgin polyester bottle grade IV around 1 to a recycled IV only 0.8, you immediately see, let's say, the decrease in tenacity we are reaching. So you're really losing, it's processable, but you're losing strength, and you're also reducing your draw ratio. So high tenacity, yeah, but you're already losing of your properties. Another example, another bottle grade, a similar trend. So you see, yes, it's processable. High tenacity polyester fibers are becoming a challenge. If you then think about recycled polyester textile material, you see here the blue curve. So are we able to stretch in the same ratio? Not at all. Is it processable? Yeah, but we are not reaching high tenacity anymore. So for there, we need to have something to control viscosity to make sure we can go back to those high stretching ratios and high tenacity fibers. So what can you do? There are different options. Often a challenge, what is the best way to proceed depending on my material? Let's say, first of all, very important, and that's something you always need to do even when working with virgin polyester. Try to mean, even with the virgin polyester, if you would have water in your polyester and water works as a scissor cutting down your polymer chain, will also have it. So therefore, drying before processing is very important. You can also work with some gassing system to make sure that all those small scissors, water scissors in there are being removed. Of course, with material, because it's already destroyed during your lifetime, then you need to think about how to restore it. Probably the most easiest is the last one. You add You add an additive. Additive is trying to couple those molecules, those small ones together, that you have back a long one. Adding it means you have to add something that's the additive that you add. Will cost some money, but you see you have an IV increase, very short time in something. That's the reason a lot of machine constructors are looking at those other two technologies. And what is the other two? SSP, LSP, so it means solid state or liquid state polymerization. So what we're trying to do there is we try to increase after our processing, we try to increase. Liquid state, it means in the melt. Solid state, it means we have our pellets, and we try to reprocess in an SSP equipment, high pressure, high temperature. But you see here, it will take some time. So typically 24 hours, a batch react step, while the LSP, you see in minutes, this can be coupled after your extruder and try to do it in line with your extruder technology. This is how also the machines are reconsidered it, especially for our textile materials, because it's very important to work on this IV enhancement of your materials. This is an example where we worked with chain extenders. The idea was to have, again, an IV of 1. 1 is already quite high. It will mean to go back to high tenacity. For a classic monofilament fiber, we are aiming something like an IV of 60, 65. Also, depending there on your end application, you might need an IV value. But here, the aim was to go back to an IV value of 1. So here we worked with different combinations, let's say additive, and you could see, depending on, we started very low, suitable for multifilament extrusion, not suitable for high tenacity, and with different, let's say, chain able to increase the IV value. So yes, important thing, we can improve processability, fiber tenacity. Yes, we have some effect. The challenges, of course, like I said, it's an additional cost, but some other challenges, sometimes difficult to control because you don't know how many of those chains you're really trying to extend, and there's still some risk of inhomogeneity and gel formations to be taken into account. Therefore, I think another solution would be more to go to the LSP and the SSP. And here an example where we started from a post-industrial waste material. So fiber waste, shredding and compacting. And then the first route was to go to regrind and try to you immediately see here a red line. This was not possible because I had a too low IV. You see here 47, so it was not spinnable again on our multi-filament extrusion line. Even after blending with some virgin material, yeah, we have some material with a very low tenacity. So we tried the 3 different routes with some chain extenders, some solid state polymerization, and also with some LSP. This is not on the graph. So we tried to process, and you can see, just as an example, modified with the SSP, the IV is again above that 60, quite close to the reference virgin polyester, and also with respect to tenacity, we could reach similar properties as a virgin polyester fiber. So yes, with those routes, you could go back to melt spinning, we could go back to a weaving or a knitting platform, and we produced again a new fiber that went back into a curtain up. So it seems, you see, definitely it is important to control viscosity. So here the key takeaways, of course, but that's always when you work with polyester, and there at this moment difference to restore SSP, LSP, chain extender. So it's we rethink those technologies and try to restore materials. Of course, also here, like I was saying, depending on your input quality, depending also on your requirements, do you need to go back to high tenacity, just multifilament? You might need to fine-tune, and you need to match your solution to your specific application. Okay, let us now look at the third challenge, contamination. Yeah, what could it be? I think it's a combination of all different things that might end up into your fiber. It means, yeah, some particles from other materials. You can have dust contamination, cotton fibers that might in there. Also working during fiber spinning, you're working with finishes, spin old, fiber material, different dyes. So combination, all this might also have quite some influence on your material. If it's something you can have pressure built up and let's say everything that's blocking, unstable processes, degradation, discoloration, that viscosity things might occur. If you think about solution, of course you can say I try to wash everything and then I have a lot of contamination that are already being removed. That's a solution, but you will not be to wash cell waste that will come back, so that's definitely not a solution for it. So therefore we are looking at, let's say, everything removal technologies on one hand, but also can we do something inline, and inline, yes, we can work with some systems and filtration lines to remove some contaminant. But still important, this becomes very important. So we have things like the digital product passport. I think you all heard about it. Sorting will be important. Based on digital product passport, we will be able to really make sure it's a polyester-rich stream. It makes sense to put here in a thermomechanical recycling line something with 80% of cotton. That will never work. We need, let's say, as much as possible those monomaterial streams. So this will still be the key enabler, and that's the reason why also the textile strategy, the digital product passport, the ESPR, the eco-design guidelines will also be important for the future. We'll not zoom into on this here today. But if you want further information on those things, please contact us and we can definitely help you on those. Just as an example, I say we need some kind of monomaterial waste stream. This is 100% polyester post-production waste. IV, you see here, was quite good, so we really believed this was a material we could process back into fiber to fiber. But when trying to do this, suddenly we had, and when looking further into detail in them, you see here that black fiber appearing. This is definitely not a polyester, so there was some wool contamination into our material. And even a small fraction of this wool contamination was causing a lot of problems and was our filters. Then okay, you can say we can try to filter out it, so we try to filter it out with a filter 20 micrometers and 40 micrometers, but take into account you're trying to filter out. This is a rheology of a virgin polyester. These are the rheology curves of the same polyester, recycled polyester with some filtration. So you see a drop here in your viscosity. So this is coming back to the other challenge, viscosity. So we are here filtering something out to reduce contamination, but we are having an impact on our viscosity for polyester due to shear effects. So then you need to restore this back to this. So you need to boost again your viscosity of your polyester to make sure you go back to a virgin material. So you see all those different actions you're taking, they are going hand, because one action you're taking here to filter something out is affecting some properties of polyester, and you need to work in restore of your polyester chains to avoid this contamination. Another example, just looking, this is on this project we are running for the moment, where we try to evaluate the difference between something that's mass colored, so you add something into your polymer matrix, and a batch dyed material, and then we try to process it into different recycling routes. First important thing that you can see, if you have something that's mass colored, you keep quite your color. If you have something that's mass dyed, that is batch dyed, and you try to reprocess, we are losing some of the coloring, and even after certain loop, the colors completely change. So yes, this could maybe be a way to reduce color of something batch dyed, but just to be honest, we also lose a lot of properties. So is this still processable? No, because at the end we didn't have any bobbin left anymore, so it was too unstable, so we had a lot of contaminations. So this is something we will show you then in the Re-APS, how to deal with something that's batch dyed, and are there possibilities to remove this color. Another way to remove it, and this is already a side jump to something that you can work with some purification technologies. And this example, we use CO2 as an, let's say, alternative green solvent to remove color and to remove dyes, to others, even to remove flame retardants, to also remove plasticizer out of PVC. So it's quite versatile what we can do with CO2 as a green solvent. Just to show you one example, this is the impact of the spin finish that you apply during your fiber extrusion process, which is of course important CO2. So we applied from 0 to 0.1% of, and the color is maybe not very well seen, but this is a whitish one, and you see if you try to recycle this material, due to the presence of the spin oil, it was yellowing. So your polyester material due to the spin oil. What we then try to do is use supercritical CO2 as a kind of pre-treatment to remove the spin oils, and up to 95% of the spin oils could be removed. So with this you can go back to a white virgin polyester grade instead of something that is a little bit yellowed due to the pre-clean. So the next thing is try to upscale this to really industrial scale to make sure that we can also prove this on an industrial scale. So key takeaways here. Yes, we can try to purify materials. Think about filtration, but take into account filtration might have some impact on your viscosity. So you need to also look at both properties together. Work with degassing for some volatiles. The supercritical CO2 might be an emergent technologies, but later on more on this. But will still stay important. Sorting, separation technologies, tracers, digital product passports, it needs to go hand in hand, because otherwise we can't just throw in anything we think about in an extruder. This will never work. Let's now have a look, where are we at industrial scale, because we can indeed show you some nice examples what we are doing, but you might have tons of materials that you would like to reprocess. What is already feasible today? So if you look at the state of the art, you see here quite some important names. Big Machine, NGR, BB Engineering, Starlema. They're really thinking about, okay, they have quite some expertise, plastic recycling. What now about textile materials? And then first important, of course, textile materials, the bulk density is the challenge. So integrated shredders, compacting units into one device. That's definitely something they are working on. So the preparation of the material to get them homogenized, because in other challenges are working with textile materials compared to plastics. Working on high vacuum degassing, filtration, and then this is also the important one, the combination the SSP and the LSP react to make sure that you control your viscosity with some inline monitoring and even some inline spinning. So all of those, maybe coming back to EREMA, because also later on in the Re-APS project, so we are evaluating two different lines. So there's one located at CETI, which is, if I'm correct, an Interrama line, while over here we have a Vacurema line. Small difference in features, but also to show you what are the difference into the different technology. You also here see the pure. This is the integration of a shredder with, let's say, an automatic feeding. So also there evaluate the different features of the different recycling lines. As an example, what is already happening today, this is an example of 100 polyester closed loop recycling fiber to fiber, So Oping has put on the market what they called their circular mattress, working with 100% structure. So they are, of course, they are still using the steel wires. It's a pocket spring mattress. So the steel wires, they are out end of life, but all the rest is, let's say, polyester based. Also the glue, the Niagara glue that is being used to combine everything, it's a polyester base, so the mattress looks like. They take it back, so it's doing the collection, the sorting into all those individual fractions. Together with Indurama, there's reprocessing it back to staple fibers and recycled polyesters. With TBE, it goes back to non-woven, and those non-wovens go back into a virgin polyester mattress. So this is an example showing you that there is already some closed loop systems popping up where we are trying to work with polyester. Examples, this is from the project Reclaim, a joint venture between Salvation Army Trading Company and Project Plan B. Capacity 3,000 per year for the moment, and you see here the different feedstocks they are accepting. Which is already showing you they're also here, they're not taking everything in, they really select on those materials because they know it will be high polyester rich. It's a controllable waste stream so that they can really make sure that it's mainly polyester that is coming in. You see they are using the pure loop technology of here. So here with the shredder device, also some let's say vacuum degassing, and then they try to reprocess the material 3,000 tons per year. The example is a cooperation Oerlikon Barmach, probably for people in fiber spinning, that's a well-known name, met Reo Eco. So they have built a thermomechanical recycling in China. With today even a high capacity, 250,000 tons filaments are fiber to fiber being produced each year. Maybe an important remark also here, if you look at input waste material, you see bottle flakes, white textile waste, so they are really dedicated white textile waste material, and also some film. So they are not using only textile waste, so they're also blending it with other polyester waste streams. You see here the different steps, so the drying, the homogenization, because they use those different waste streams, and they also go back bottle, films, fibers, but already quite high volumes, and they're also claimed to expand those capacity in the near future. Then looking more locally in Europe, some other known examples, so Antex in Spain, looking both on thermomechanical, also of polyester, going back to fiber spinning. Re-Up, its cooperation also here, the Netherlands, Turkey, Movi in France, setting up a thermomechanical recycling line for polyester. Nurel is not polyester, but I just want to show it here. It's also a Spanish company, they are focusing on polyester. We also have the polyamide 6. We also have the expert. I don't find the name. Polyamide 6 recycling. No, the company that also the Aquafil. Thank you, Philippe. Yeah, the Aquafil. But this is then going back to the monomer. It's not recycling. This it's the thermomechanical. So for polyamide, I think there are definitely already quite some nice solutions on the market. For polyester, everybody is looking what is the best way to move forward. Another example in France, Mapea, also working at this moment already end of life, garments, trying to reprocess them. And then another example, but also to show you it's not only in the polyester field we are working on thermomechanical recycling, is an example of Beaulieu. So the rewind carpet, it's a polymaterial, so a needle-felt polyprop carpet. It can go back into carpet, but also they are looking at other applications. So also looking at 3D printing and molding for some waste material, so that it's not only going back to carpets. They try to close the loop as much as possible, but also looking at, let's say, open loop applications. So this proves that indeed we are moving forward. We are moving to some more industrial scale. Some companies are really investing in those technologies, but it will stay important to look at your input materials, quality, and you need to tackle all those challenges. As a last point, because I think I'm already a little bit over time, how can we help you? I think we work on all those different fields. So what we have here in-house, the shredding, the compacting, repalletizing, and the melt spinning, but to show you where are the hurdles and where we really want to make the differences. We are evaluating the SSP, but more on let's say, the labs to boost the IV. We have the Vacorema line here in-house, and this is what we will do, the comparison also in the Re-Up process, where we have the high vacuum reacting system, able to indeed to remove to make sure that the viscosity is well controlled. And of course you can work with chain extenders in line during compounding, and you can add them if you want. If we look the other hand at contaminations levels, we can work with different, let's say, screen melt filtration units. On the Vacorema line, we both have the degassing, but also over here we have the ultra-fine filtration units able to filter out at this moment 15 micrometers filter size are used out as much as possible of those contaminants. Will this solve everything? No. It's also the reason why we have now resubmitted a new project also looking at reactive extrusion to make sure that also maybe high fiber, cotton fiber rich materials we might also be able to deal with will be work for the future. I think just as a last example, just to show you why it is important, this is an example where we tried to compare a classical processing on let's say a twin screw compounding line, a conventional process with the Vacorema line. And you can definitely advance the Vacorema line, so the high vacuum degassing, the IV control and the filtrations. You are able to maintain the property of your virgin materials. If you try to process this on a conventional line, you see a huge drop in your property. It's definitely worthwhile to look at those challenges and try to prevent all those contaminations into your machinery. So this is of course a combination of work, so not all has the result of Re-APS will be shown here. It's a combination of different projects, just I try to show you, to trigger you a bit more and to show you some examples. So definitely yes, there is a possibility to work on thermomechanical recycling of polyester, but with the different challenges to tackle. But I think with all of us here together, we can make a difference, try to go to monomaterials, try to sort them in a proper way, and then try to find some solutions for those. So thank you all.
So good afternoon again. I am Fran Maenhaut, research at Centexbel, and together with CT, this is Milda from CT, we will present you the project progress and preliminary results of the Re-APS activities so far. So first, let's go quickly over what is. We are a Belgian research and technology center, mainly supporting the textiles and plastics industry. Our main activities are R&D, testing, but also services. We are located all over Belgium. First of all in Ghent, where we have a chemical, physical and fire behavior testing lab, and also a coating and finishing platform. Then here in Courtrai we have a polymer characterization lab and also a melt processing platform. And then we also have a seat close to where we have a microbiology and comfort lab and a platform for technical textiles. So
Hi, my name is Milda. I'm an R&D project manager at CETI. CETI is a research center that is really at the interface between research and industrial application for textiles. We are located not very far from here in the north of France, in Tourcoing. We were started in 2012 and we've got about 20 employees, and we have quite a big park of different platforms, of different machines that we can use. We are specifically based on everything that's both experimentation and industrialization of a variety of different processes. And we are really dedicated to innovation, prototyping, technological realization, and industrial transfer. So here you can have an overview of all of our technical platforms. So we go everywhere from compounding and spinning fibers to non-wovens, yarn spinning, wet spinning, different kinds of recycling, and we also have a characterization and performance measurements platform. And within our recycling, we usually talk about it in two sort of main technologies that we have, which are the mechanical recycling machinery and also the thermomechanical recycling, which is what we're going to present today as part of the Re-APS project.
Already introduced earlier, the core objective of this Re-APS project is to move from raw materials into textile materials, so going from fabrics and ultimately to filaments and fabrics again. In this sequence we can classify two main parts. So first of all we can talk about the preparation phase, and then followed by a thermomechanical recycling phase. It is very important for this technology to be successful, to have a very good input stream. So the quality is very important. Here you can see a view of the main materials that we want to tackle in the Re-APS project. So we start with monocomponent polyester, and then we will look at 100% polyester with additives like flame retardants, dyes, and so on. Then we will later on, to make it more complex, we will look at blends of polyester with other thermoplastic polymers like polyamide, and then at the end the aim is to go to even blend other materials like. So then we look at post-industrial and post-consumer materials, and as you can see, we start with least complex materials and go on to the most complex materials. So let's start with the preparation phase. When we receive new materials in the project, one of the first and most critical steps is a thorough characterization. So often we already got a lot of information of the providers, the company, but for us it's very important to check it internally to ensure accuracy, but also to eliminate potential inconsistencies. So in practice, we have the characterization includes several analyses. For example, material identification, where we analyze the composition of the material. Also, we do a screening of elements like flame retardants, other disturbing elements. And we can also do then also thermal properties are important for our thermomechanical recycling. So with TGA we can analyze degradation temperature, and with DSC we can analyze the melting, crystallization and Glaston temperature. Later on we will also do entropy measurements, as Isabelle already explained. It's very important, and we will do in the next slides. So first of all, we have the impact of the processing on the IV, so on the intrinsic viscosity. Here you can see a material, we were able to process it, but you see that during the processing, the melt came out of the extruder quite, it seemed to have a quite low, and this also was confirmed by the IV measurement we did. So you see that by going from a fabric to a pellet, the IV drops significantly. This is one of the major challenges Isabelle already mentioned, and we want to. So to address this issue, we look at SSP, solid-state polymerization, as a method to restore the intrinsic. So again, in the table, by going from a fabric to shredding, eventually packing, and also it drops. But what we also see is that by SSP treatment, the IV increases partially. So that's already a nice result, because we know that are imported for the processing later on. Also, we did some other IV and SSP other materials, and we see that for a range of initial values, so for all the, we were able to increase the IV with SSP treatment, and also by a longer duration of the SSP, the IV increased. So that's a nice result that we had, and it's also a good practical guideline to estimate the required duration of SSP for our materials. So another related was what Isabelle also mentioned, the input and the feed for materials. The bulk density is very important, and what we mentioned with some materials was we try to feed tissues and also filaments, and for the tissues we actually observe some issues. It's fairly smoothly, and also if we went on with this, no major unusual issues were seen. The bone was slightly more yellow, but again there was some spin. So that's the same answer that Isabelle already mentioned, and the tensile strength was comparable to virgin polyester. Then when we went on with filaments, we had feeding difficulties into the screw. So by tamping, the material became compacted, and this leads to a poor uptake of the screw. So we had an irregular feed and no stable strand formation, as the strand continuously broke in the water bath. So we had to stop the trial, and it's not processable in this way. So conclusion of this is that processing of tissues was in this difficult feeding of filaments, and to go on to overcome this challenge in the Re-APS project, we decided to the filaments at CT before processing. Another key aspect that we investigated is contamination removal, also already introduced by Isabelle, and those can negatively affect both the processing but also the final properties. And within the project, we have explored CO2 extraction at lab scale as an innovative approach to contaminants. So here you see a first result. We want to try to remove colors and see the effect on different types of textile, but also different types of printing. And actually, it was quite promising at first sight. So here you see a digital printed woven textile, both in soft shades and dark shades. I don't know, it's very good visible, but actually both were quite good removed from the color. So it was successful. Then we also did on the same type of material, so a woven textile which was digitally printed, but this time the darker blue color. So here you can see after different times in the supercritical 2 structure. So after 60 minutes you can see that the color was already a bit removed, but not completely. And after 90 minutes it was a lot better and after 2 hours as well. And here we took samples of the extracts of the supercritical 2 machine. Yeah, you see that here it's very dark blue, and by extracting longer times, you see that the color that we extract becomes less. So probably by extracting longer times, we will even become more white. So this was already interesting. Try this other materials. So here we test digital printed non-woven textile. This had a good result. The removal of the color was almost 100% effective. And then we went on with non-woven textile but screen. And here we saw that the removal, it didn't change anything after 2 hours. Even the material took up quite some extract. As you can see in the next slide, you will see it. There we have extracts, and the first extract that we tried to take after 20 minutes, there was even not a lot of extract, so it was all in the material. So until now, digitally printed materials seem to be effectively de-inked with ethanol as co-solvent, but for screen printing it seems ineffective ethanol. Then we had one less material that I tested. All are woven solution dyed textiles with the same extraction parameters that we used before. And the yellow, you can see that yellow and the green one are quite good. Yeah, the color is removed, but for the blue one it is still not completely removed. I have to say that all materials were in the same trial, so probably the bluish ink that you see over here comes from the blue one that was in the same trial. And also the extract, so that's what I mentioned before, that the extract in the first time was not so much. We see that it starts very dark, but still at 2 hours it's quite blue. So we think that extending this trial by longer times, maybe we can also de-ink the blue solution dyed woven textile more. So next steps are we want to expand the trials that we did. So for example, go for longer times for these materials. And also we want to look at the removal of frame retard. And later on we want to have larger scale trials to see if this really helps the further processing. The removal really helps the further processing of us. So now I give the word to Milda. Yes.
So I'm going to introduce the work that we've done at CETI with the thermomechanical recycling. As we have spoken before in the amazing presentation by Isabel, that explained exactly what goes within the process. Just a reminder, we are they're undergoing a full process. The RPET, which is our recycled, which can be used for melt spinning and non-reduction. The idea is to incorporate these RPET new textiles in different industries. The CETI is the work package 4 leader. So here we are talking about thermomechanical recycling and applications within the industry. In among our platforms, we have a compound, a twin extruder, which you can see over there on your left. And here is a picture of our Arima line. And this allows us to go from fabrics. Within the applications in textiles, there are 2 sort of main routes. There's either melt spinning or non-woven production. Within the melt spinning, we first take the rPET granules, a monofilament or a multifilament, which can be monocomponent, and then we can go from that onto fibers and be knit or produced via the dry lathe process, or we can go the melt non-woven route, spun bond and processes to go from our pellets into new fabric. Well, here you have a representation of our Arima line. You can see that we have our starting material, example of one of the materials in our case study. It goes through different units. There's the conveyor belts with the metal detector. That's the process in case there are any metals present in the sample material, which could cause it. We have the bit known as TU. This is an important 3 letters. Remember, because I'm going to refer to it quite a lot within. Then we have unit 3, which is the extrusion screw, where we have 4 different temperatures allow us to polymer, and we have a fuming screw to remove compounds. We then have a filtration screens where we can change use. And then we have an underwater pelletization unit, which is to obtain, this is an example of the pellets that we obtained from that starting fabric, which can then be used to make materials. The work package 4 approach can be separated in different. We have sample with partnership with Centexbel. We then have the recycling and characterization of the specific measurements to see how not just by the IV measurement, but to see also how the material under different shear rates. And then we have an evaluation by spinning. So the way that we have decided at CETI is to first go through a monofilm to establish how the behave, and then enhance the properties of the recycled polyester by incorporating it into a bicomponent spinning, which is in the core sheath formation. So first we do the recycled in the core and virgin in the sheath, and then we invert this configuration. And then the last step, the application for textile structure. So we are in the same that you saw before. We go from the least complex samples to the most complex samples. And the samples up to now, the 3 case studies that I'm going to present, the A, B, and C. So case study A was a white woven fabric, so it's the least fabric that we have tested. Case study B is 100% same kind of fabric, but with a black fabric. And the third case study is a variety of different samples, still mainly polyester-based. One is a post-consumer fabric, so it has all of the added washing cycles, etc. We are talking about 100% fabric, samples of the fabric, and what it's like right before the aroma machine, and the pellets that were obtained. We had the influence of color, so here we have a very, very white and pristine fabric, which is the machine, and the brown, the process. A note on the viscosity. Here you can see the results and comparison to 2 reference virgin polyester samples, and the viscosity optimism of processing on our melt lines. In terms of the evaluation via melt spinning, this specific fabric, it was process and spinning, and when we started to core sheath configurations, so as I mentioned before, the virgin PT is either center or in the outside of the polymer. You can see the 2 different configurations in the pictures here. One of the main takeaways, we saw that the virgin polyester would define the mechanical properties component. And another interesting observation that we had, so for example here you can see that one of the virgin polyesters here in this, one of the virgin compatible, the recycled, and we were actually not stretch ratios, for example. Study B, so once again we have 100% poly, but this time we have a color, and so here the material was black, so the granule as well. In terms of the capillary rheology analysis, we can, this time, the obtained pellets have a match to the virgin PT pellets, and so we already, just from seeing this when we compare this fabric. No component spinning, we could obtain a 5 points per filament denier, and a variable based on the different draw ratios that we were able to apply. Something that was very interesting in terms of the color, and therefore information about the possible application of this fabric, this polyester, is the configuration. You can see the change from 100% virgin PET all the way to 100% recycled bobbin, and all the different impacts of having different ratios of recycled and virgin within the same bobbin. We actually saw a few color differences, I don't on this slide, but whether the recycler in the core or in the sheath is something that could eventually have an impact on the depth of the fabric. This is in the future work of the project, and we saw that based on how much recycled put. These are our most recent. This is a post-consumer sample, and different here you can see how very heterogeneous it was. There are some glitter, there are some highly densely woven supports on the other side. We have some sport type textiles, some fleeces, and some knitted sample have stick properties. We can therefore, just from visual analysis, not polyester, an interesting mixture of possible contaminants into our process. We did manage to put it through the machine, and it did not stop our machine, so that's quite positive. But we have obtained these granules on the bottom, but the viscosity is not very good. So on your left, you can see a comparison we removed from the preconditioning. This is before the extrusion and melting of the polymer, and then you can see the actual obtained, and you can see that the viscosity did decrease, so that makes sense that after application of the different temperatures we have a lower viscosity. But once again, if we compare to the viscosity of our virgin polyesters on the graph on the right, we are very, very low. We have not spun the material yet, but this would be a very good candidate for different studies such as... just to summarize, the conclusions from these 3 case studies are that we have observed a recycle. This has an impact on, therefore, our next step from the materials that we have in-house. We have seen there are different compatibility between the recycled polyester and different virgin polyesters. Therefore, it's always interesting for both of them, some affinity of one of them to the virgin. There is, we can see that the incorporation of virgin polyester in bicomponent configurations helps us boost the mechanical piece of the fiber. We can see that there is a clear influence of the recycler on the color of our fibers, so that is going to have an impact on the dyeability of our textiles. And we have already seen that the drying conditions of our pellet have an impact on which helps us ensure that we are limiting the prior to this. In terms of our future work, we are continuing with case study C. We have just passed through these results. We are now going melt spinning in the way that we did other fabrics. We are then going to consider the chain extenders and boost our viscosity level and make more higher T fibers. And the next case study would be a post-industrial PET and 6 blend, which would be moving along. If you're looking at the table that we had before, this would be the next step. And thank you.